All right, solubility product. It might sound nasty to begin with, but it's actually just equilibrium. We're just looking at equilibrium constants again. And truthfully, solubility product tends to be a little bit easier than the equilibria that we've been looking at so far. So, solubility product is just the equilibrium constant for dissolving ionic compounds in water. Starting it as a solvent, dissolve it in water, and what's the equilibrium constant? So, for example, look at this one right here. If we've got silver chloride solid, I'm going to put water above the equilibrium arrows just to say we're dissolving in water, but I don't want this as a reactant in my equation. Well, that will make Ag plus aqueous plus Cl minus aqueous. Note, if you're going to write the equilibrium constant expression for this, it's always products over reactants. So you would expect to be the concentration of Ag plus times the concentration of Cl minus divided, this is a solid. Solids are not in our equilibrium constant expressions. Therefore, the equilibrium constant expression, K equals concentration of Ag plus times the concentration of Cl minus. Since this is the equilibrium constant for dissolving this, we call this equilibrium constant the solubility product. So the solubility product is merely the equilibrium constant for dissolving a solid into its ions in water. And since our reactant is only going to be the solid, that's all we will ever have on the reactant side is the solids. It will never be in the expression. The KSP expression is always just the concentration of the two ions to their stoichiometric power. That's why they call it the solubility product, because it's concentration of the cation times the concentration of the anion, the product of those two. All right. Note, if you recall solubility rules, you might remember that you don't expect AgCl to be soluble, because remember all chlorides, iodides, and bromides are soluble, except if the cation is silver, lead 2 plus, or mercury 2 plus. And so we'd expect that silver chloride is not very soluble in water. And when we look at the solubility product, we find it as a KSP of 1.77 times 10 to the minus 10, which means this equilibrium lies way, way, way to the left, which means if it lies way to the left, that means it does not dissolve into ions very much at all. So that follows. Note, make sure we remember all our rules of equilibrium. Say we had CaF2 solid dissolving into Ca2 plus. Recall it dissolves into Ca2 plus 2F minus. Therefore, the KSP is a concentration of Ca2 plus times the concentration of F minus squared. Don't forget our rules of equilibrium constant expressions. If we have a 2 here, that means we have to square this concentration. Okay, but let's start with the easy stuff first. Let's go back to our AgCl. How much silver chloride will dissolve in the water? What will be the concentration of silver chloride if you put that solid and try to dissolve it in water? Well, we know not much of this will dissolve, but I want to know how much Ag plus and how much Cl minus we have at equilibrium, which means ice tables, ICE, draw your line. Note, this is a solid, so we never have to worry about the amount of AgCl we put in there. If you're putting solid AgCl in there and you're going to put enough that you have some solid left over, so you know that all that can dissolve has dissolved, you can tell because there's still some solid left over in your container, in the solution, then it's just standard ice table. We don't need the amount of AgCl. We just have the Ag plus starts at 0. Initially, no Ag plus before any of that silver chloride dissolved. No Cl minus, plus X. We have X and X here. Note, KSP is a concentration of Ag plus times concentration of Cl minus. 1.77 times 10 to the minus 10th, our KSP, is X squared. X is 1.33 times 10 to the minus 5th molar. That's our concentration of Ag plus, concentration of Cl minus. Since this is a 1-to-1, this will be our molar solubility of AgCl. For every 1 AgCl, we get 1 Ag plus. For every 1 mole of AgCl, we get 1 mole of Ag plus. Here, in terms just of our reaction, if this reaction went 100%, but it doesn't because it's equilibrium. But this is our molar solubility here. 1.33 times 10 to the minus 5th will be the molar, how many moles per liter is dissolved of AgCl. Okay, what if, there we go, molar solubility here. What if we then looked at the molar solubility of CaF2? It's not a problem. Ice table again. We don't worry about the solid, 0 calcium, 0 fluorine. But note it's X and 2X here. So at equilibrium, we have X calcium, 2X fluorine. Note our KSP equation, we got the squared. So 1.46 times 10 to the 10th equals X, amount of calcium, times our amount of fluorine, 2X squared. Note 2X squared is 4X squared. 4x squared times x is 4x cubed. So 1.46 times 10 to the minus 10th equals 4x cubed divided by 4. Take the cubed root of that, and you get x equals 3.32 times 10 to the minus 4th. Molar, and that's our molar solubility of CaF2. Since x is for calcium, we have a 1 here and a 1 here. We look at x is our molar solubility, not 2x. X's here. Something to note though, the KSP for calcium fluoride is 1.46 times 10 to the minus 10th. For silver chloride, it was 1.77 times 10 to the minus 10th. These are kind of similar, 1.77, 1.46, both times 10 to the minus 10th. However, note that the molar solubility of silver chloride is 1.3 times 10 to the minus 5th, where for calcium fluoride is 3.2 times 10 to the minus 4th. Calcium fluoride, that's times 10 to the minus 4th, and 10 to the minus 5th. Calcium fluoride is about 10 times, over 10 times more soluble compared to AgCl. So when you're looking at molar solubility, while your KSP values do say, okay, this isn't very soluble, KSP 1 times 10 to the minus 10th, not very soluble. KSP 1.4 times 10 to the minus 10th, not very soluble. Note that the molar solubility of calcium fluoride is greater than silver chloride because of this squared factor here. Because of the 2x, we've got that squared factor here. You have to take into account. So while solubility product and molar solubility are related to each other, they are not equal to each other. Okay. Well, that's nice, but let's look at Le Chatelier's principle. Let's look at the common ion effect. Here's two questions here. One we've already done. That's why I picked it as the first one. You dissolve AgCl, plenty of AgCl in water, such that you get a saturated solution. What's going to be the concentration of silver ion in solution? How much silver ion is left in solution? But what if instead of dissolving the AgCl in water, you dissolved it in 0.1 molar sodium chloride solution? Now what would the concentration of silver ions be in solution? Good news, turn back a page and you found we've done the first one. The concentration of silver ions in a saturated solution of silver chloride is 1.33 times 10 to the minus 5th molar. But what if we did? What if we dissolved it in sodium chloride, 0.1 molar sodium chloride? Well, note we're going to set up our ice table like we did previously, initial change equilibrium for this reaction, and we're not going to worry about the solid silver chloride. Before any dissociation of silver chloride, note we had no silver, but since we dissolved it in 0.1 molar sodium chloride, which is a strong electrolyte which dissociates 100%, we know we have 0.100 molar chloride. So the solvent that we dissolved it in had chloride, which is what silver chloride dissolves into, dissociates into chloride. So chloride is our common ion. Well, what does Le Chatelier say happens to an equilibrium if you start with one of the products already there? Before this reaction occurs, we already have some product. Le Chatelier says this reaction will not go as far to the right as you think it should. This chloride ion is going to keep the equilibrium more to the left. So just by knowing Le Chatelier's principle, we would suspect that silver chloride will not dissociate nearly as much because there's already chloride, which means we would expect the concentration of silver to be less. than if there was not chloride already present. Le Chatelier's principle tells us you start with chloride, you should expect less silver here. Common ion, Le Chatelier's principle says it's going to push the equilibrium more towards the left. But let's do the calculation. Since there's no silver to begin with, a little bit of silver chloride will dissociate in X plus X here. So we got X and 0.10 plus X for our equilibrium concentrations of silver and chloride. Plug into the KSP equation. KSP equals X times 0.10 plus X. Question, can we ignore this plus X here so we don't have to worry about quadratics? Absolutely. This is 10 on 1.77 times 10 to the minus 10th. We know X is going to be very, very small compared to 0.1. Therefore, we ignore this plus X here, and so we get 1.77 times 10 to the 10th equals X times 0.1, and this math became super easy. X equals 1.77 times 10 to the minus 9, which is our concentration of silver. So note, when you dissolved your silver chloride in 0.1 molar sodium chloride, we end up with 1.77 times 10 to the minus 9th molar silver ions. If we dissolved it in pure water, we had 1.33 times 10 to the minus 5th molar. 10 to the minus 5th, 10 to the minus 9th. A whole lot more silver went into solution when we dissolved it in water compared to when we dissolved it in sodium chloride. And that's exactly what we'd expect from Le Chatelier's principle if we actually started out with some product. This is the common ion effect. That common ion that both our solvent and our dissociation had in common means that the dissociation is not going to happen nearly as much. All right. And related to the common ion effect is how pH affects solubility. Remember, pH is the concentration of H plus, which is related to the concentration of OH minus through Kw. Meaning, if any of our things that are going to dissociate, any of our solids that will dissociate have OH minus possible or H plus possible, then pH is going to affect that. And we've already looked, if it's got H plus, well, that's just acid dissociations. But if we have OH minus here as one of our ions, our common basic ions, OH minus, S2 minus, carbonate, CO3, 2 minus, means this. For example, if we add magnesium hydroxide solid, it will dissociate into Mg2 plus aqueous plus 2OH minus aqueous. No problems there. But what if you had magnesium hydroxide and you added NaOH to raise the pH? Or you weren't dissolving magnesium hydroxide in pure water, you were dissolving it in pH 10 water, meaning sodium hydroxide is in there. We know at pH 10 that there's more hydroxide than H plus, so the pH is raised. Well, hydroxide is the common ion here. So if you tried to dissolve magnesium hydroxide in NaOH, less magnesium hydroxide would dissociate. You get less magnesium in solution. Common ion effect. But what if you added HCl to lower the pH instead of basic solution or neutral water? What if you added magnesium hydroxide into acidic water? Well, we know that HCl reacts with OH minus. OH minus from this dissociation will react with HCl to make H2O and Cl minus, which means because our HCl reacted with our hydroxide, there's less hydroxide around. Well, what does Le Chatelier's principle say is going to happen if there's less product? Yes, more magnesium hydroxide will have to dissociate, will have to dissolve in order to create more hydroxide to reestablish the KSP equilibrium, which means magnesium hydroxide is much more soluble in HCl than in water, and it's much less soluble in sodium hydroxide than in just pure water. All right, so let's end this video here, and we'll pick up the next time with KSPs and looking how that affects one of our favorite Gen Chem 1 topics, precipitation reactions.